When it comes to the origin of the universe, the first reaction in many people's minds is the Big Bang. Currently, this is the most widely accepted theory, suggesting that about 13.8 billion years ago, the universe exploded from a singular point with maximum density and extreme heat, continuously expanding over a long period and evolving to its current state. Therefore, according to this theory, scientists always believed that the early universe was a chaotic place, filled with masses of matter that could form crystals, all very disorderly. However, there are still many hypotheses surrounding the somewhat mythical story of the birth of an entire universe. Among them, the most frequently asked question is, are we alone in this vast space? If not, what lies beyond the borders, where light and all space come to an end? Could it be another universe or a different epoch? Looking back over billions of years, these scientists can observe the evolution of our universe in astonishing detail. From there, they open the door to a new realm with 5 hypotheses about what might exist beyond the boundaries of our universe. What is the observable universe? If we want to know what lies beyond the universe, we first need to determine the nature, shape, and size of the universe. If we were to envision a specific state of the universe, many people would choose the image of a large, spherical ball, round and filled with matter. The outer shell of this spherical ball is the boundary, and nothing can surpass it, not even light. Isn't that peculiar? If the universe were a solid, stationary sphere, such a scenario would never occur. However, through the process of observation, humans have discovered that the universe is undergoing expansion at an acceleration faster than the speed of light. That's why we develop and maintain the concept of the observable universe. The observable universe for humans on Earth is a region of space that encompasses all matter, objects, and phenomena that humans, with astronomical instruments, can observe at present. It includes systems of galaxies, galaxy clusters, stars, black holes, and more. Since we can only see things when their light reaches us through emission or reflection, we can never observe beyond the farthest distance that light can travel during the existence of the universe. This means that the observable universe is expanding, but it has a limit. This quantity is sometimes referred to as the Hubble volume, named after the telescope that has provided us with the farthest views of the universe. We will never be able to see beyond that boundary. So in terms of intentions and purposes, it is the only universe we have ever interacted with. People often estimate the overall size of the universe by estimating the number of galaxies existing in observable space. According to NASA, the number of galaxies in the universe has increased tenfold compared to previous estimates by scientists. Utilizing the Hubble Space Telescope, NASA has discovered more galaxies. Around the 1990s, based on the information gathered, humans only estimated about 200 billion galaxies in the universe. Using a new mathematical model, the research team calculated and deduced the number of galaxies that even the most advanced astronomical telescopes have not detected. About 90% of galaxies in the universe cannot be seen because they are too faint or too far from our planet. Therefore, the current number of galaxies in the universe may have reached 2 trillion, 10 times the previous estimate. According to scientists, the universe is expanding, and our Milky Way galaxy has around 100 billion stars. If multiplied by the figure of 2 trillion galaxies, there would be approximately 200,000 trillion stars in the entire universe. Even this number is likely too small, as we may discover many more galaxies in the future with further technological advancements. Hubble volume. Like everything else in physics, our universe strives to exist in the lowest possible energy state. However, around 10 to 36 seconds after the Big Bang, cosmologists speculate that the universe found itself in a false vacuum state. When searching for the actual lowest point of the vacuum energy in a fraction of a moment, the universe is believed to have inflated by a factor of 1050. Since then, our universe has continued to expand, but much slower. We observe evidence of this expansion in the light from distant objects. As photons emitted by a star or galaxy travel throughout the universe, the space's expansion causes them to lose energy. By the time these photons reach us, their wavelengths have shifted towards the red end of the spectrum, corresponding to the distance they have traveled. This is why astrophysicists talk about redshift as a function of both distance and time. Light from these distant objects has traveled for so long that when we finally see it, we are observing those objects as they existed billions of years ago. Redshifted light allows us to see objects like galaxies when they existed in the distant past, but we cannot see all events that have occurred in our universe throughout its history. Because our universe is expanding, light from some objects is too far away for us to see. The physical nature of that boundary partly depends on a quantity of both space and time called the Hubble volume. Here on Earth, we determine the Hubble volume by measuring something called the Hubble parameter, H0, a value related to the apparent recession velocity of distant objects with their redshift. It was first calculated in 1929 when Edwin Hubble discovered that galaxies in the distant cosmos seemed to be moving away from us at a rate proportional to the redshift of their light. The result was a contentious revelation that the universe is expanding with an acceleration faster than the speed of light. This is also one of the fascinating consequences following the theory of general relativity that we've discussed extensively before. Revisiting the issue of the observable universe, in cosmology, a Hubble sphere is the region of the universe observable surrounding an observer, where objects are receding from the observer at a speed greater than the speed of light due to the universe's expansion. However, the volume of the Hubble sphere is not identical to the observable universe. To understand this, consider that as the universe ages, distant light has more time to reach our detectors on Earth. We may observe objects that have accelerated beyond our current Hubble volume because the light we see today was emitted when they were still within it. To be precise, our observable universe aligns with what is known as the particle horizon. The particle horizon marks the distance to the farthest light that we can currently see, the photons that have had enough time to be within or catch up to our gently expanding Hubble sphere. And how far is this distance? Over 46 billion light-years in every direction, bestowing upon our observable universe an approximate diameter of 93 billion light-years, or over 500 trillion miles. At this point, I have a few clarifications to offer. We should not equate the concept of the particle horizon with the concept of the event horizon of the universe. The particle horizon encompasses all events in the past that we can currently observe. On the other hand, the event horizon of the universe defines a distance where an observer in the future will be able to see ancient light emitted by our tiny slice of time today. In other words, the particle horizon refers to the distance to objects in the past whose ancient light we can see today. The event horizon of the universe refers to the distance that our current light can travel as the remote regions of the universe accelerate away from us. Thanks to the expansion of the universe, there are regions that we will never see, even if we were to wait an infinite amount of time for their light to reach us. But what about areas beyond the reach of today's Hubble telescope? If that sphere is also expanding, can we see objects at its boundary? This depends on which region is expanding faster, the Hubble volume or the parts of the universe just beyond it. The answer to this question relies on two factors. One, whether H0 is increasing or decreasing, and two, whether the universe is accelerating or decelerating. These two ratios are closely related, but they are not the same. In reality, cosmologists believe that we are currently in a time when H0 is decreasing. However, due to dark energy, the rate of expansion of the universe is increasing. It may sound counterintuitive, but as long as H0 is decreasing at a slower rate than the rate at which the expansion of the universe is accelerating, the overall motion of galaxies moving away from us continues to occur at a faster pace. At this moment, cosmologists believe that the expansion of the universe will surpass the modest growth of the Hubble volume. Therefore, even though our Hubble volume is expanding, the influence of dark energy seems to impose a rigid limit on the ever-increasing observable universe. What will exist outside the Hubble volume? Royal Astronomer of the UK, Martin Rees, suggests that the theory of eternal inflation could lead to a fourth Copernican revolution. After Copernicus proposed that Earth is just one of many planets orbiting the Sun, we realized that the Sun is also just one of countless stars in the Milky Way, and other stars also have planets orbiting them. Further discoveries led us to understand that the Milky Way is just one galaxy among myriad galaxies in an expanding universe. And now, even the entire universe might be just one among countless universes. Although there is no conclusive evidence for the accuracy of this theory, eternal inflation could help address one of the most challenging issues in modern physics. Physicists have long sought a theory of everything, or the grand unified theory, a set of laws, or even just a simple equation that can be used to derive all other physical laws. However, the possibilities they explore outnumber the fundamental particles in the universe. The string theory, a viable candidate for the ultimate theory, has an enormous number of solutions, one followed by 500 zeros. Each solution establishes its own set of physical laws, and there is no clear reason to choose one over the others and disregard the rest. The theory of multiverse inflation frees us from the burden of choice. Each universe within it may have different physical laws determined by one or a few solutions of string theory. In the universe we inhabit, fundamental physical constants seem finely tuned to allow for the existence of life. For instance, slight variations in electromagnetic forces would render atoms unstable. A mere 4% change in this force would halt all nuclear reactions in stars, essential for producing carbon atoms for living organisms. Similarly, there is a delicate balance between gravitational forces contracting the universe and dark energy expanding the universe to allow stars to form without the universe collapsing. These mysteries have led many to believe in the divine hand of God. However, if the multiverse inflation is true, every set of physical laws could be valid somewhere, providing an alternative explanation. In each universe, there would be a suitable configuration for a form of life to develop. Intelligent beings would then strive to understand their fortunate circumstances. In universes with configurations unsuitable for life, no one would ponder these questions. This is an example of the anthropic principle. If things were not as we observe them, we wouldn't be here to ask questions. For many physicists and philosophers, this seems like an evasive way of addressing the issue. How can one test these assertions? However, unless you have an alternative explanation for the natural laws, some will argue that every occurrence is due to the hand of God. Astronomer Bernard Carr boldly stated, "If you don't believe in God, you should believe in the multiverse." Astronomers suggest that space may be infinite, with stuff, energy, galaxies, etc., distributed somewhat similarly to the observable universe. If this is true, it has some incredibly strange implications for what lies beyond. Beyond the Hubble volume, you would not only find many different planets. Eventually, you will find everything imaginable. This also aligns with the saying, if you go far enough, you'll find another solar system with an Earth exactly like ours in every aspect, except this morning you had cereal instead of eggs. And in another case, you skipped breakfast. And in yet another, you woke up early and robbed a bank. In reality, cosmologists believe that if you go far enough, you'll find another Hubble volume entirely identical to ours. There's another version of you out there reflecting every action you take, about 10 to the power of 188 meters away. It may sound far-fetched, but the universe is infinitely mysterious, hiding things beyond the limited perception of humans. In astrophysics, the dark flow is a non-random component in the theoretical peculiar velocity of galaxy clusters. According to standard universe models, the motion of galaxy clusters relative to the cosmic microwave background should be randomly distributed in all directions. However, a group of astronomers led by Alexander Kashrinsky, analyzing 3 years of data from the Wilkinson Microwave Anisotropy Probe, WMAP, using the Sunyaev-Zeldovich dynamic effect, found evidence of a galaxy cluster flow surprisingly consistent with a velocity of 1,000 kilometers. This flow was discovered shifting towards the Centaurus and Hydra superclusters. This aligns with the orientation of the Great Attractor, a gravitational anomaly first discovered in 1973. However, the gravitational force of the Great Attractor is believed to originate from a massive galaxy cluster called the Norma cluster, located about 250 million light-years from Earth. In a study in March 2010, Kashrinsky expanded his work from 2008, using the results of WMAP's 5-year data instead of the 3-year data, and doubling the number of observed galaxy clusters to 700. The research team also divided the cluster catalog into 4 slices, representing different distance ranges. So far, researchers have listed its effects up to 2.5 billion light-years and hope to extend the catalog further to double the current distance. Some researchers suggest that this motion could be remnants of the effects of an unseen region in the pre-inflationary universe. Telescopes cannot observe events earlier than about 380,000 years after the Big Bang, cosmic microwave background, when the universe became transparent. This corresponds to the particle horizon at a distance of about 46 billion light-years. The matter causing the net motion in this proposal lies beyond this range. Thus, in some way, it exists outside our observable universe. However, it would still be within our previous light cone. This motion challenges any predictions about the mass distribution throughout the universe after the Big Bang. Some have speculated that large structures outside the Hubble volume might have caused gravitational influences. This implies that the structure of the infinitely extending universe beyond our sight is non-uniform. For these structures themselves, they could be anything in the literal sense, from aggregations of matter and energy on scales we can hardly imagine to strange curved paths conveying gravitational effects from other universes. Based on the data, Laura Mersini-Horton and Rich Holman observed that some anomalies predicted by both theories related to interactions with alternate universes, or when the reference frame of the CMB does not match the expansion frame of the universe. In 2013, arguments were made that data from the Planck satellite of the European Space Agency showed no statistically significant evidence for the existence of dark flows. However, another analysis by Fernando Atrio Vallandera, a member of the Planck collaboration, argued that this data was consistent with previous findings from WMAP. Mainstream media continued to show interest in this idea, with Mersini-Horton claiming that the Planck results confirmed the existence of a multiverse. This could be an effect of a sibling universe or an entirely different space-time region compared to the observable universe. Data from over 1,000 galaxy clusters have been measured, including clusters located up to 3 billion light-years away. Alexander Kashrinsky argued that these measurements show a stable flow in the universe, not due to statistical luck. The only thing we can say for certain is that the world in a very distant place is very different from the world we see on Earth. It's either another universe or a different space-time structure. Infinite bubbles. Talking about what's beyond the Hubble volume might be a bit tricky because it could still be the same universe or just a part of it that we cannot see. It would have all the same laws and physical constants. In another version of the story, the expansion of the universe after the Big Bang led to the formation of bubble structures in the space-time fabric. Each bubble is a region where the expansion halts along with the rest of space and forms its universe with its own set of laws. In this scenario, space is infinite, and each bubble is also infinite, as you can fit an infinite number of infinities within a single bubble. Even if somehow you could cross the boundary of our bubble, the void between the bubbles is still expanding, so you'd never reach the next bubble no matter how fast you travel. The simplest multiple universes model stems from the assumption of the universe's infinity. While we can't confirm this hypothesis, we can't deny it either. According to this idea, the universe is divided into many separate regions, each unable to detect the others due to the vast size of the universe. The estimated age of the universe is about 13.8 billion years, so anything beyond the 13.8 billion light-year range is indistinguishable. Each such region can be considered its universe. If this is true, there would be countless universe islands similar to the universe humans are familiar with, and there must be many worlds similar to Earth. It may sound implausible that atoms would arrange the same way to create a copy of Earth, or a copy with only minor details different. However, if the infinity of worlds is real, such a place must exist, and there could be many. With the same logic, there should be a copy of our universe very far away, at a distance of about 10 to 10, 118 meters. However, it could also be a finite universe. In the case of an infinite universe, matter could only concentrate in a corner of the universe, meaning other places would be mere emptiness. But, as of now, there is no clear evidence for this hypothesis. Another model of multiple universes, which can be seen as a solution to the fine-tuning problem without resorting to the anthropic principle, is the natural selection of universes proposed by Lee Smolin from the Perimeter Institute for Theoretical Physics in Waterloo. In 1992, he suggested that the universe could reproduce and evolve like living organisms. On Earth, natural selection preserves organisms with useful traits, well suited to the environment for growth and development. Smolin argued that a similar phenomenon occurs in the universe, called cosmic natural selection. The idea is that a mother universe can give rise to many child universes within it. The mother universe achieves this through black holes. A black hole forms when a massive star collapses under its gravitational force, squeezing atoms together until reaching infinite density. In the 1960s, Stephen Hawking and Roger Penrose demonstrated that this collapse is akin to the reverse of a mini Big Bang. This idea led Smolin to believe that a black hole could be a Big Bang, giving birth to a new universe within it. If so, the new universe might have slightly different physical properties than the universe containing the original black hole. This is analogous to random genetic mutations leading to offspring that differ from their parents. If the physical laws in the child universe allow for the formation of atoms, stars, and life, it would also have black holes with the potential to give rise to new universes. Over time, the number of such universes would increase, becoming more prevalent than universes without black holes or the ability to reproduce. This is an intriguing idea, suggesting that our universe doesn't have to be a product of sheer randomness. If a finely tuned universe, capable of forming atoms and life, is surrounded by untuned universes, cosmic natural selection implies that the finely tuned universe will gradually become the norm. This model has a significant advantage. It can be tested. We can search for the specific conditions of this universe conducive to black hole formation. However, so far, there is no evidence that black holes can give rise to an entirely new universe. As we delve into the realms of the bizarre and the mind-bending, one thing becomes clear. Our understanding of the universe is just scratching the surface. The 5 weird theories we've explored today challenge the very fabric of our comprehension, pushing us to question the limits of existence itself. Whether it's the idea of a cosmic hologram projecting our reality, parallel universes existing in tandem, or the universe being a mere simulation played out in some advanced cosmic computer, these theories invite us to embrace the mystery that shrouds the cosmos. It's a reminder that the universe is not a stagnant entity, but a dynamic, ever-evolving enigma that keeps us on the edge of our intellectual seats. As we navigate the vastness of these peculiar speculations, it's essential to approach them with both curiosity and skepticism. The quest to unravel the secrets beyond our universe continues, fueled by the human spirit's insatiable thirst for knowledge. Whether these theories turn out to be flights of fancy or the keys to unlocking the universe's deepest truths, one thing remains certain. The cosmos will keep us guessing, inspiring generations to come on a journey into the great unknown. So, as we conclude this exploration, let's marvel at the mysteries that lie beyond the universe and eagerly anticipate the discoveries that await us on the cosmic horizon.